Alright, welcome back to the channel. Today we are going to be talking about chemistry honors. In lesson 12.4, we focus on ionization constants. An ionization constant is the equilibrium constant for an acid or a base. For an acid, it's Ka. For a base, it's Kb. You have to take the ionization constant of the products of the ions over the reactants, which is the, bond, the ionic bond between the two. So an H2SO4 dissolving into 2H2 plus and SO4 2 minus, you have H plus squared, SO4 minus on the top, and H2SO4 is on the bottom. The significance of the Ka values indicates the degree of ionization for an acid. A small Ka value indicates more molecules and ions in a weak acid. Large Ka means more ions and molecules, strong acid. In this case, 1 will determine if it's a weak or strong acid, if it's a lot or a little bit. Kb value is the same concept. Large Kb indicates a high concentration of hydroxide ions or a strong base. Small Kb values indicates a low concentration of hydroxide ions and a weak base. We will also be talking about lesson 12.5 in this video, an important history lesson for molecular theory. Oh, and by the way, 12.4 is as far as the test goes. So, yeah. So the Arrhenius theory is that you need H plus ions to have an acid and OH minus to have a base. Bronsted-Lowry broadens it up, though. A substance that can donate a proton is an acid, and a substance that can accept the proton is a base. They worked on this separately but concurrently. So when you have HCl, you have the proton donor. H2O is the proton acceptor, so you have Cl minus and H3O plus. So water is acting as a base because it accepted the proton. But when you have H2O and NH2 minus, H2O is the proton donor and NH2 is the proton acceptor, so water is acting as an acid in this case. A water is amphoteric. It can behave as an acid in one reaction and as a base in another reaction. HSO4, HCO3, NH3, H2O can also act like this. So they donate protons in the presence of strong bases, and they accept protons in the presence of strong acids. So these aren't very weak or strong if they're amphoteric. A conjugate acid-base pairs is ones that are reversible, like HCl plus H2O with Cl minus and H3O plus. The conjugate acid always has one more proton than its conjugate base. HCl, Cl, H3O, H2O, H2SO4, HSO4, HCO3, Cl3. So for example, HF, the conjugate base of it is F. H3O, H3PO4, the conjugate base of it is H2PO4. Conjugate acid of Br is HBr. S, HS. So if a conjugate acid is strong, its conjugate base is weak. Conjugate acid is weak, conjugate base is strong. A weak conjugate acid is not able to donate a proton readily because its conjugate base holds on to it tightly and is strong. So H2SO4 is a stronger acid than H2O. If OH minus is a strong conjugate base, then HSO4. Now the Lewis theory broadens up even more. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So when you have BF3 plus F to BF4 minus, that is actually an acid-base reaction according to Lewis.